Hello everyone, and welcome to this second session of midas NFX webinar for Nonlinear Static Analysis. I am Cyprian, the International Technical Manager for Europe, and I'm glad that you joined today's session as well. I see a lot of people who came to the first session of the webinar, and we will begin right away. I'd just like to confirm that today is the session 2 of this webinar. So this is the main summary, what we talked during the first session, the introduction about the nonlinear, the procedure and the options in the nonlinear analysis, nonlinear geometry. Today we have a lot of topics to talk about: the nonlinear material, elastoplasticity, hyperelasticity, contacts, and some good advice to do better the nonlinear analysis. So it will be a very useful webinar, and I've prepared a lot of concrete examples just for you. So I'll go very quickly on the slides I presented last time. So there's 3 types of nonlinearity: geometric, material, and contacts. I explained last time what is the difference between linear and nonlinear. I show you some examples. I told you when you should consider nonlinear analysis. Then I talked about the method to calculate the nonlinear results, so the curve, the increments, the load steps. As well, I talked about the error tolerance, the different types of methods you can use in nonlinear static, and the buckling. So I talked nonlinear buckling and how you can use the arc length method in order to get better results when you have some buckling in your system. Then I presented the procedure to do the nonlinear analysis. So it's actually very similar to the linear analysis sequence. So except a few difference during the material assignment, the assignment of the boundary condition, and the analysis case creation. So I presented all that. So the video is on YouTube. So if you didn't see that, you can watch the video, and you'll have, again, you'll remember what I said. So today we have a lot of things to speak, because nonlinear analysis is very large topic, but also very interesting. So I'll begin with the concept, which is the elastoplasticity, so the nonlinear material. So in linear analysis, the deformation of the material is elastic, but in nonlinear, the plastic deformation of the material can be estimated. So this is why you have different types of nonlinear analysis material: elastoplastic models, hyperelastic models, creep models, and it is important to select the right material model when you are performing such analysis. So elastoplastic model is so I'll present it right away. What are these models? So basically, elastoplastic model is what we use to analyze the nonlinear material types. Hyperelastic models is specific type of nonlinear elasticity. So when you have rubber material in your system, for example. And the creep is a special type of stress which appear in your model when due to the time. So when the time is passing, you have some kind of stress which is created inside the model. So this is called the creep. Now the basic, let's say, there's no really a basic curve, but for a steel you have a curve which can seem a bit like that. So this is elastoplastic model curve. So you have several areas in this curve. You have the elastic area here on the left. You have the perfect plastic area. You have the deformation on the hardening and the necking. So you can understand it like that. When you are in elastic domain, the stress increased until you reach the yield stress. At this step, there's a small step of perfect plasticity. So in this step, the yield stress is not changing, but you have some plastic strain which is created. And after that, you have some increase of the strain, so what is called hardening, and finally the necking and the rupture. So when you are doing elasto-plastic model, you also have to think about when you have some loading and unloading in the model, and NFX manage this very well using the subcases, so you can perform this loading and unloading in the same analysis. So this is quite useful. Now the yield criterion. So maybe you heard about the Tresca model, the von Mises model. So Tresca is explained like that. So the maximum shear stress should be superior to the simple tensile test yield value divided by 2. So this is the definition of the Tresca. And if you represent it into diagram, it will look like that. Now the von Mises model is based on the triaxial stress state shape deformation energy that should be superior to the deformation energy of the simple tensile test yield value. So it gives you a formula like that. And the same if you draw the curve, it will give more a circle than the Tresca model. Okay. So I'm just reminding some basic concepts, let's say, that are useful for such analysis, especially if you want to understand why you need to use nonlinear material. So let's talk about also the shape deformation energy. It's important to understand that when you have a model which is in triaxial stress state, so on the 3 axes you have some stress, what really causes the yielding inside this model is the torsion, which it's the torsion and the actually you can divide this triaxial state into 2 states. One is called the isotropic volumetric pressure. So in this state, the stress on all the surface is the same, so on the 3 axes is the same, plus the difference of this one. So you understand easily how you can get such division. So the stress which causes the yielding and the deformation is the second one. So the isotropic volumetric pressure doesn't cause any yielding. If you're wondering why, you can imagine that you put some ball inside the water, so the volumetric pressure of the water around the ball cannot make any yielding inside because it's the same pressure over in all directions. Okay. Now let's talk about the hardening models. You have isotropic hardening model, kinematic hardening model. So basically, isotropic hardening means that the yield stress increase of the same ratio for the tension and the compression. So if you're doing tension or if you're doing compression, it will increase the same way. So it has a consequence that if you draw the graph of the stress strain curve, you'll see that it will stay centered around the middle of the graph, of the middle of the axis. So the point on the middle will not move. You have the kinematic hardening model. So difference is that in this model the yield stress domain is constant. So the domain is constant. So in this case, this is the plastic deformation actually moves along with the center of the yield stress domain. So you can draw an axis like that, and you'll see that when you have loading and unloading of your model, the main stress will remain on this axis. Now if you think in 3D, you have no more a path like that, but you have a surface. which is called the yielding surface. So it's the same models, the isotropic hardening, the kinematic hardening. So the isotropic hardening model in 3D will actually extend, so the yield surface will extend from the initial surface. So as soon as you get plasticity, your yield surface will extend. But if you do the kinematic hardening, it will move. So it will not change the total volume, but it will move along one or another axis. So this is the difference between the two models. Now you have also something called the Bauschinger effect, which is actually which refers to a property of the materials where the material stress and strain characteristic changes as a result of the microscopic stress distribution of the material. So for example, an increase in the tensile yield strengths occur at the expense of the compressive yield strength. So actually it's a kind of combination of isotropic and kinematic model. So you can think about this. So it extends and it moves at the same time. I will pass over the engineering stress via the true stress. So you can check the book if you want that. Okay, now let's talk about NFX. How do you define all these models? And I think a lot of you are wondering about that. So first of all, the perfect plastic model. Well, this is the most simple type of model to be defined in NFX. The reason is that there's only to define the yield stress, so only one parameter to be defined, and you can have your model. So if you go in the material tab, Elasto-plastic, and here you have the perfect plastic, you just enter yield stress value and it's okay. So for those who are wondering why I don't always use this model, this is because it's a big simplification. So you have always to remember that it's real simplification. So perfect plastic is only valid on a certain range. So you cannot use it to all kind of nonlinear thing. Now the bilinear model. So bilinear model is actually a kind of cinematic, no, not kinematic, it's the first one, the isotropic. It's a kind of simple isotropic model. So you have it like that. So you have two ways to define this model. So you have you can define the plastic hardening curve or the stress-strain plastic hardening function as well. So in NFX, so you have two ways to define the stress-strain function or the plastic hardening. So what is the difference? The stress-strain function type actually defines all the curves, so from 0 to the final failure. So here you have to define all the curve. But the plastic hardening function defines only the parts which is plastic. So you don't define the elastic range in the plastic hardening function. So this is a difference. There's another difference is that if you look at the numbers here, you see that the two curves, this curve, the stress strain, began at 0, and then the plastic range began at the plastic yield strain 0.001. When you are using plastic hardening, the plastic strain is 0, so it's not 0.001, it's 0, and you have the yield stress. So you have to remember that. Now, if you want to make a real, let's say, curve of the material, well, it's simple. You just have to paste all the data of the stress and strain in this stress-strain data curve. So you can paste it from Excel, for example, and you'll get the model. So it's a multilinear model because it's actually an approximation of a lot of smaller segments. Okay, before going to the next section, let's do a simple application of that. So let's go into NFX. So if you have questions during the session, please ask. I am here for that. Okay, let's open a new project. So I am in the analysis mode. So I'll begin in 3D millimeter. And what we'll do is a tensile test. So you know the basic test where you take some sample and you apply some tensile on it. So first thing is let's hide the guiders because it will be better to view that. Now I'll import my model. So let's search where is my model. Tensile test. Okay, it's not here. Okay, let me check. Let me search for 1 second. Okay, I found it. Okay, here it is. So this is, I've got the axis, it's better. Okay, so this is the sample that I will use to make this analysis, and the first thing I'll do is just to define the material. So let's go into here, material, click on the material, and let's add a new material, so it will be isotropic. Now let's choose Elasto-plastic because I'll use this what we just learned about the nonlinear material. So tensile elastic modulus will be 16.8573 and 0.209 for the Poisson's ratio. So I'm not considering the gravity, so I don't need to enter the mass density. And I'll use the plastic hardening curve. So I'll go into plastic hardening function, and I will go into Excel and simply paste the data for my analysis. So I click on copy, I come back to the software, I click in this area and I paste the data, and I get my my plastic hardening curve. Now I click on OK, and don't forget to assign the curve by clicking on here, otherwise you will have an error when you run the analysis. Okay, so I created my material. Now I have to create a property which is going with, so it will be 3D property. Let's call it tensile tests and assign the material I just created. Okay, done. Now let's prepare the model. So you see that it's actually a symmetric model, so I don't need to mesh all the model. I could do it, but it will take more time, and it's very, very important to limit the number of mesh you have in the model when you are performing nonlinear, because you know that nonlinear takes some time to perform. So first thing I'll do is to create a symmetric model. So I will use the tool in NFX to divide my model. So I use a solid divide. So I check here, and I will divide by 3-point plane. So I'll just click on the model to define the different planes, the different points, and I see the preview. Okay, looks good. Now let's do it once more, because I have two symmetry in this model. So up, I check here like that. 1, 2, and 3 points. Okay, now I got it. And what I'll do is just delete the part that I don't need, so I delete them like that. Now I got my model, and now I have to do the meshing. So what I'll do is so what you will do basically is just select the 3D mesher and mesh it automatically, but there's a better method than that, because you see that there's also symmetry in rotation. So in order to create the best mesh possible, which is also something important in the nonlinear analysis, I'll create manually the mesh. So I will create a 2D mesh first. I will use the map face option to map the face here, and let's choose dimension of 2. Let's preview the size, looks good. Click on OK. So now I got 2D mesh on this face, and what I will do is to revolve this 2D mesh to create 3D mesh. So I will delete the source mesh, select the rotation axis, and use an angle of minus 90, and let's say 7 division. Let's look at the preview. Let's zoom a bit to view. Looks good. So if I increase the number of division, let's say if I choose 10, it will look like that with smaller mesh, but actually it's a bit too small, so I just choose 7 and click on OK. Okay, now I got my my mesh, so I can begin to assign the boundary condition to all that. So let's click on the right view like that, and I have to assign some constraint because of the symmetry. So let's go in the Advanced tab, select the face here, and this is, so you can look at the axis here, X, Z, so X, Z, symmetric plane, preview, apply. Let's do the same on this plane, X, Y, preview, and apply. Okay, now I got this. So you see there's a lot of small symbols, so it's slowed down a bit the pieces, so I will just hide the labels. Now let's assign another constraint to the left side. So the left side I will just block it, so I will fix these parts. So I'll fix these nodes, fix. Okay, and let's apply some displacements to the other part. Displacement, select all that, and it will be displacement of 7 millimeter. Okay. Now I'm ready to create the analysis case. So let's go in Analysis, General, let's give it a name, Tensile Test, and choose Nonlinear Static Analysis. I'm still doing static because we didn't learn about dynamic, but it will be subject of next webinar maybe. Okay, now have to go on the subcase control option. So here the mesh I created is defined, the boundary condition, the load, I don't have any contact. Okay, so I have to create on this subcase control, and here I have some very important options which are uh, useful for nonlinear, so don't forget to check the geometry nonlinear option to consider the large deformation. 60 number of increments, and I think it's okay. So click on OK. Let's save the model. Okay, and I can run the analysis. So let's wait a few seconds that the software give us some results. So each time you are doing nonlinear analysis, you have the graph of the maximum displacement versus the load scale factor which appears. So right now you can view the convergence in real time. Okay, so I have my first iteration, you see, which converged with one iteration, and you have the error tolerance here, the maximum translation, the maximum stress. It's useful to check these data each time you're doing analysis, because you see that if the maximum stress, let's say, is 0, then you see there's a problem somewhere and my analysis is not going well. So you can also check the results during the analysis, which is very useful. So to do that, you go in the tensile test analysis case, you right click with the mouse, click on open the result file, and you select the result file of the analysis you are doing, click on open, and it will automatically open the increments that are that have been solved. So you see I have already some kind of result. What I will do is to stop the analysis here and to load the data from the model that I've already run. It actually not take long, only 300 seconds, but my computer here is a bit slow, so I'd rather show you directly the results. So tensile test, okay. Let's wait a few seconds that it loads the results. Okay, now you can see that you have total translation. So each time you're doing nonlinear analysis, don't forget to put the scale factor to real, because it would have no physical sense to let it to some scale factor. So now you have the real displacement, so you see the extension of the tensile stress. So you can see, for example, von Mises stress and view the stresses here. So you have the maximum stress at the middle. So let's say if I would like to draw the curve of the maximum stress, let's say, you can use the extract tool and check solid stresses. Then you check the type of stress you want to extract. So here it will be solid stress, let's say von Mises. I will extract the maximum stress and click on table, and then I will get the result into a table. Okay, and after that I select the column and I choose to show the graph. You can also export it into Excel if you want to use these data later. And now you have a view of the increase of the stress during the load cases. So when you increase the load, you have the increase of the stress. And you view very well that you have some, let's say, elastic range, and then it goes on very small perfect plastic, and then it increases. Okay, so this is all for the first example. Now let's come back to the slides to talk about the next topic. Okay, so the next topic is hyperelasticity. So this is also very interesting. So actually it's usually used to analyze the rubber material. So in rubber material you have an incompressibility which appears because of the complex link between, let's say, the polymers inside the model, inside the rubber, and they are different from metallic materials because rubber material can be subjected to large deformation, but they will always come back to the initial shape, so it's a kind of nonlinear elasticity. So, and because of these properties, they are used in a lot of applications, like the vibration damping properties. Rubber material are absorbent and excellent to remove the dust, for example, soundproof. So they are used, for example, you can think in between the door of a car and the car body, so to a lot of application for the rubber materials. Rubber material can be simulated with several types of models. So you have hyperelasticity that I will talk today, but you have also some other types like viscoelasticity, which is actually the physical property of the material which depends on the time. And so the hyperelasticity, the way to simulate that is to use the strain energy function W, that I'll explain what it is, whereas the viscoelasticity is to considers two types of effect, the creep effect or the hysteresis effect. So NFX can also simulate the creep if you are interested in such application. Okay. Now, what is an hyperelastic material? So, as I told you, material loaded and submitted to a deformation of 500% can recover the original shape. And as a nonlinear material, nonlinear analysis have been used, of course, but in this specific case, the principle of superposition can be used as for linear analysis. So this is a specific case because it's linear. So it's nonlinear material, but it's a nonlinear relation, but it's a linear type of elasticity. Oh, sorry. Okay. So the properties of hyperelastic material. So stress can be derivated from the strain energy density function. Stress are assumed from integration of the strain. And midas NFX provides several types of model, like called the Moonley-Rivling polynomial Ogden-Blatsko, to calculate and to evaluate the strain energy function W. So the best way to approximate the strain energy density function is to use the stress-strain experimental data. So strain energy function, strain energy density function W can be expressed in a different way in function of the model you are using. So if you are using a polynomial model, it can be written like that as a combination of polynomials. So these coefficients you see, A, I, J, are some coefficient of the polynomial. So they depend on the degree of approximation that you will give to your model. So if you are doing one order, it will be much more simple than that, first order model. And Gy, G2, G3 are a constant of the material. So one one specific case is the Moonley-Raveney model. So if you look at the formulation, you see that actually it's the case when NA is equal to 1. So it's the same than the polynomial equation, but with NA equal to 1. Now, I will not talk in details about all the model, but you can view here the formula about this. This is the Ogden model. Difficult to express clearly the behavior of the material by using the energy function by the principal strain G1, G2, G3. So material constants are not directly expressing the physical property of the material, so mole function is expressing it. It's rather complex model. And Blatzker model can be used also for the foam materials, for example, which is incompressible nature is too strong, so material constants are reduced to the initial shear stiffness only. Now, if you want to calculate the J1, J2, J3, you can do like that. So you are thinking about your undeformed shape L1 with dimension L1, L2, L3, and after deformation the dimension will change, and it will change in lambda 1 L1 and lambda 2 L2 and lambda 3 L3. And if you can, using these formulas, you can calculate G1, G2, G3. So you imagine that performing some test on your model. So if I deform it like that, so what will be the dimension, and then you can evaluate these constants. So the basic tests that are used to evaluate the constant of this hyperelastic material are the uniaxial tensile test, the biaxial tensile test, the simple shear test, the pure shear test, and the volume change test. So I give you some photos. I will not explain all that. I believe that those who made some experiments in the laboratory know very well about such kind of tests. So in NFX, how do you assign the hyperelastic material? Well, it's very convenient thing is that you can enter directly your experimental data in the software, and it will approximate your model. So you don't need to calculate manually, let's say G1, G2, G3, or the strain energy and everything. You have some result, let's say, to do it. So what you do is to click on evaluate the experimental data, then you enter the type of test that you did. So it can be one of the tests I just talked about. Then you create the curve corresponding to the data of this test, and you can fit the test data, and you get the evaluation of the equation that will be used for the material. So after that, this is the hyperelastic material window. You have the coefficients, which are actually corresponding to the, you can see here the A10, A01 here. This is the two coefficients. And the volume change material constant is calculated. Now, there's something that you should be aware about, is that there's something called the hysteresis effect. So actually, when a rubber material composed of complex chains of polymer is loaded and unloaded, you still have some kind of loss of energy due to the friction that occur between the molecule. So if you look at the curve here, you can think of the loading and unloading. The energy loss can be represented like that. So it means that basically, if the rubber material you are using never had some kind of deformation, it will the curve of this material will change after a few cycles. So this is called the hysteresis effect. And you have also the stress softening, which describes the stabilization of the stress strain curve from the initial shape to a stabilized shape after several cycle loading. So if you load it, unload it, load it, unload it, at the end, after a few cycles, you will get some kind of final shape of this curve. So now some precaution to take for hyperelastic analysis. The thing is that I talked about low order model and high order model, but what you have to know is it's not always the high order model that is the more is the best. Why? Because sometimes when you approximate with a high order model, you see that there is a local negative curve in local negative slope in this curve. So you have some kind of instability in this, and when you perform the nonlinear method, you see it's a bit like the nonlinear buckling that I talked about. At this step, it may not converge. So you should be aware that sometime when you go to low order model to high order model, you may have such kind of problem. So you have to be careful and check that the curve is not like that. Okay, let's look at an example, because you're wondering, I think, how to do that in the software. Well, I have a good example for you, which is the rubber boot seal. So let me open the model again. I hope I will find it this time. Okay, boot seal, here it is. Okay, so maybe you know what it is. So it's the kind of in the car the stick of the I don't know how it's called in English, but okay. Now, okay. So the first step to so if you look at the model is composed of some 3D parts and a plate, so composed of 2D model. And here the kind of white links here are rigid links. So these are used to concentrate all the nodes, let's say, degree of freedom in one point. So if I constrain the point at the middle, I will get don't need to constrain all the points of all the nodes. Now, okay, the color of this rigid link is a bit too, I cannot see it very well, so I'll just change the color here. Let's put it to blue. Okay. Okay, it's not perfect. Let's put it to yellow, maybe. Okay, better. Okay, now first thing to do is to create material. So let's create our rubber material. So to do that, let's go into rubber material. Okay, let's go. I don't need. Okay, isotropic. Then choose hyperelastic. I will call it rubber. Now you need to enter the mass density, which is 1 power minus 8. And after that you have the icon which is evaluate the experimental data. So I click here, and now I can enter my experimental data. So simple tension and compression test. So actually I already defined these curves before. So I will not show you how to create this curve. I show you in the previous example. So it's simple, you paste your data from Excel. So my first curve is the result that I got from my experimental data, my simple tension and compression test. I click on add to add it here. Second one is equibiaxial tension. So the curve is biaxial. Click on add. Now, okay. Now I have two. So you see, you have the polynomial here type. So here you can define the order of the distortional and the order of the volumetric. So here I will just put 1 and 1. So it will be the first order polynomial. And click on fit to the test data. So I hide the test that I didn't define. Okay, so now you have two types of, you have the simple tension and you have the equibiaxial. You see the curve in green, the curve in red is the curve of my experimental data that I entered. The curve in green is the curve which is fitted, so it's a first order curve, so it will be fitted like that. Experimental curve, so this is the second test. So so if, let's say, I change the polynomial to second order, let's say in distortional, I add it, fit the test data, you see that it's much more close from the curve here. So here, if I look at this curve, I see that it's okay, I don't have any negative slope, so I can use this model as well, which may be more accurate. Okay, so I click on close, I will save the data and close. And now you see that the coefficient needed have been automatically calculated and entered here. So I'll uncheck the Poisson's ratio because it will, the value will be taken from the D1. And I click on OK, and I now have my rubber material. So now now that I created this material, let's assign the properties here. So I see that rubber property is defined, so I will modify this property, and okay, the material which is actually assigned is the rigid material, but I will assign the new one I created, the rubber material. And the 2D property of the plate is the rigid one, okay, 1 mm plate. Perfect. Now let's assign the constraint and the boundary condition to this model. So first thing to do is to constrain this rigid lengths together. So let's click on constrain, select this node, fix, okay. Oh, I see that I fixed this point but also 3 nodes here, so I just go back and be sure that I select only the master node, fix, okay, now it's better. Now let's assign the constraint to the solid. So let's hide this part and okay, let's see the solid like that. Show only constraint, and let's pin the bottom, pin, apply, and let's look at the model like that. And here I have a symmetry condition, so advanced X, Y, okay, symmetry. Okay, now I got this condition. I have someone wondering what is this model. Well, I guess you will see when you will see the results, because now it's a bit difficult to for those who don't understand. Anyway, this part is rubber material, so this is why we'll do this tutorial. Okay, so now let's display again this part and assign the displacement to this stick. So click on displacement. Let's select the master node again, and here I will input a rotation to this stick. So the rotation is actually, the angle is defined in radian, so I will input 0.42, which is equivalent to around 24 degrees. So I can give a name to that if I want, rotation. Okay. And now one of the most important part is the assignment of the contact between the two parts. But first I'll hide the guidance because it will be better. Okay. I hide also the rigid body. Now let's create the manual contact between these two parts. So first of all, you have an option called node to surface contact. So this is very important to choose that because it's much more stable to use this type of analysis, this type of constraint when you are so now the contact type is general type of contact. Let's choose 2D element and choose the element from the stick. And for the second face, let's choose, so this is 3D face element. I will hide the stick to select this better. Okay, so now I want to select only the internal face of this element. So there's a trick to do that. So the trick is to activate this option here in the bar, which is called front selection only. So if you click on this, it will select only the elements which are which can be viewed here. So I will select all that, and you see that the element from the other side will not be selected. So this is what I want to do. Secondly, let's uncheck this option, and I don't want to check the elements from this side, so I will click here, unselect mode, and if I do that, you see that the elements have been unselected, and now I got the good selection so for the contact between the two parts. And let's click on OK. Now let's check, because we never know what's going on with the contact. So click on manual, and you see that the surfaces are well defined. So you have the master face and the master face, so which is in red, and the slave face, which is in blue. So the method I used, node to surface contact, is very important because it actually considers master and slave. If you are using the other method, surface to surface, the master and the slave are actually not important. So the software is not really considering master and slave. But in some cases this is important. So I didn't talk yet about the contact, but I'll do it right after, so you will understand what are these, what I call master and what I call slave. Okay, and there's another thing to assign to this rubber, which is the self contact, because this rubber will have some contact which itself. So this is called self contact. It will be general contact type, so I assign that. Now I'm ready to create the analysis case. Nonlinear static. Let's give it a name. Boot seal. Nonlinear static. Okay. Go in the subcase control option. Now I check the geometry nonlinearity, so you have to check this option because you'll have big deformation, so this is required. enter the number of increments, click on OK, and okay, I got it. So now I'm ready to launch the analysis. So I will open directly the solved model because on this computer it will take at least 20 minutes. So we don't have this time now. So I will open the other boot seal to show you the results. I had some question at the same time from someone asking why I don't select the faces for the constraints, but I select only the elements. Well, it's a good question. In NFX you have the choice to select the element or to select the faces from the geometry. So it happened that in this model that I opened, I actually don't have the geometry because I created this model from rotation. So I created the mesh independently from the geometry, so I don't have the geometry. So this is why I selected the element directly. But I could of course select the geometry. Okay, now I got the results. Let's look at translation. And okay, I got nice deformation. And if I look at the last step, you see that I have some, yes, really nice deformation. So you have a rotation of the stick, and due to the contacts, it's switch here. So I could look at the von Mises, let's say solid von Mises result. So it gives something like that. But actually what is important in such analysis is to check the another type of result. So I will insert analysis result to insert, which is the solid stress mean pressure. So I need to see that, so it will give me a real indication where are located the high stresses in this kind of analysis. So you see that this is much more useful for such analysis than the von Mises stress in case of hyperelastic material. Okay, so let's go on to the next slides. So the next part of the presentation will be about the contacts. So it's also a very interesting part about analysis, because you have generally a lot of contacts in a nonlinear analysis, and you want to make some contact between different parts and everything. So I'll present that. So first of all, what is the reason to use nonlinear contacts? So to use contact first. So the main reason is that you always have the way the load application is actually propagated inside the model is through the mesh. So you have an application of the load through to the nodes, but the load is propagated through the mesh, which is actually linking together your model. So this is why you can perform the analysis. But if you have, let's say, if you have two parts in your model, you can imagine that you don't have mesh between the two. So how the solver will calculate that using contacts. So if you don't have any contact, you can imagine that the two parts will enter in contact together, but they don't know when, so there will no influence of one mesh set to another, because there's no transmission of the information between the different mesh sets, which are separated. So using the contact, it will be tested at each step if it comes in contact or not, and it will be in contact when it happens. So what makes the nonlinearity phenomenon in the contact, because it's nonlinear analysis, it's nonlinear. Well, this is because you have two main reasons for that. The first is that contact boundary and contact stress cannot be guessed in advance. So the research of the contact boundary is a part of the analysis process. So the boundary of the contact is constantly searched. And the degree of the contact stress of the contact area depends on the size of the load. So the stiffness value change also non-linearly. Then the second issue is that you have some rapid change occurring in the contact force, because the contact happens at a specific moment. So just at this moment the contact increases a lot. So this is second reason. So you have different type of contact. You have flexible contact and flexible rigid contact. So if you have two bodies and the two are more or less at the same stiffness, there will be no problem. But if you have some flexible and rigid contact, so some solid which is much more stiff than one another, if you calculate the matrix of the stiffness matrix of the relation, you see that the rubber body will have very small values. So in this case, you may not get the convergence. So this is why there's some trick to tackle such issue. So the contact method which is used is called the penalty method. So to understand how it works, it's actually like that. So the first step is that you have a load application and the potential contact nodes, and then you have the other surface, and you have a certain distance of penetration. So imagine that this is the moment when you have the contact and you have some kind of penetration, and at this moment the software will test what is the distance between the two. So it will test the value of this penetration. It will put some kind of spring element between the two parts, and then it will recalculate again. So it will apply a contact force on the other side in order to make the other part come back to the other part. So this is why this uses iteration, because it's nonlinear. So in the first step you'll have a penetration, second step it apply a contact force here, so it will come back to the right, so it will decrease the penetration, and it will do that in a recursive way. So at the end you get the right contact, an accurate contact. Then you have a contact pair, master and slave. So you have what is called the master, what is called the slave. So there's a difference between the two, because the nodes from the slave contact are not able to penetrate the master contact surface, but the nodes from the master contact are able to penetrate the slave contact surface. So if I give you some example, you see that on this side, this is the master, this is the slave, so the master can penetrate the slave. So it makes like that. On the other side, the slave cannot penetrate the master, so it stopped here. So if you want to know usually how you define this master surface and the slave surface, well, usually the rigid surface, so let's say the ground, is defined as the master, whereas the other surface, the one, let's say, that crashes on the ground, is the slave surface. Because you will not think that if, let's say, your phone is falling on the ground, it will deform the ground, right? It's always the phone that will explode, but not the ground. So this is why the ground is stiff, it's rigid, so this is the master, whereas your phone will be the slave. So the contact force, is calculated like that. So it's calculated like Fc, and it can be calculated by Kn multiplied by the gravity, and you have this coefficient Kn, which is the contact stiffness, Oh, sorry, it's not the gravity, it's the gap. Yeah, J like gap. So this is the gap between the two parts. So this contact stiffness, if it's equal to 1, it will be the best, because you'll have only J will be equal to FC. But sorry, I think, yeah, J is not the gap. Again, I told some. It's the force of the spring, actually. Yeah. So you have the force which is applied here. You have some kind of stiffness between the two, and the G is the force in the spring that will be applied to make this come back. So if K is equal to 1, you'll have the real interaction, but if sometimes it's too stiff, so you have to decrease the K in order to get to have a better convergence. So basically this factor can be found in the contact parameter in NFX. It's called the normal stiffness scaling factor. So by default it's put to 1, but if you realize that the contact between your parts is too stiff, so it's difficult to converge because one part is much more rigid than another, you have to decrease this normal stiffness scaling factor in order to make it much easier to converge. Okay, you have the friction also. I will not detail about the friction. You can come back on these slides later. You have also some kind of horizontal stiffness, so it's the same thing. Now let's talk about the type of contact. You have basically linear contact and non-linear contact. In linear contact you have the welded contact and the sliding contact. So welded contact, it means that there is no separation between the vertical behavior and the horizontal behavior. Sliding contact means you have no separation in the vertical direction, but a small sliding can occur in the horizontal behavior direction. So here you have a small schema. So sliding can occur here like that, but not in like that. Now, nonlinear contacts, you have general contact and Rose contact. So general contact means that you have you can have real separation between the two parts, and you can have sliding at the same time. So sliding, so you have some friction that can be considered. Rose contact means that you can have separation, but you have no sliding. So as soon as the part enters in contact, they will stay glued. I mean, they cannot slide one and another. Okay, I'll not detail that. Automatic contact. So you have automatic contact. So if you do that, you just select the mesh set or the parts, automatic search for the contact. If your parts are too far away, you can increase the searching distance, so you inactivate the auto and just enter the approximate size of the distance between the two parts to be sure that it will find this contact. Otherwise it may not find the contact between the two parts if you have a gap. Manual contact. So in this type of manual contact, so you have master slave to be defined. So you can define it manual by clicking on the surface like I did during the example. Self-contact. So self-contact means that one mesh set will have contact with himself. So like this one, or like the boots I just showed. Contact parameters. Now these are different types of contact parameters that are applying. So you have the contact tolerance, which is important if you want to be sure that the distance will be minimal. So let's say you have a general contact, but you really want that the two surfaces enter in contact with tolerance of 0.001 millimeter, for example, so they don't penetrate one in another. So you have to check this contact tolerance and just enter the value you want to respect. Okay, and then you have some other coefficient, like the friction coefficient can be entered here. And you have some advanced contact parameters which are available. So for non-linear explicit you have some parameter here, and for the breaking weld option, so if you are doing it's a special type of contact in NFX called breaking weld. So basically it's a welded contact, but if you have a certain force higher than a certain value that you input here in your model, the weld can be broken, so it can break the weld and begin to continue. Okay, I have the last example to show you, but I don't have much time, so because it was 1 hour at the beginning. I hope you are okay to see that. Maybe I will not do the full demonstration, but I will just load the model to show you the results. Maybe next time we'll see how to do that. So this is a steering wheel. Okay, I'm loading the model. So this is, let's say, a real application model. So it's a wheel of a car. So it's symmetric, so I cut it in two. And I have a plane here, so what I want is make a kind of stiffness on this wheel to see what will be maximum stress supported by the wheel. So what I did is, first I meshed the model, then I entered some nonlinear material. Then what I did is that I defined the boundary conditions. So let's look at the boundary condition. So I have first some rigid link on this part. So all the parts will be constrained on the center of the wheel. Then I assign some symmetric conditions. So you see that this is symmetric. And I fixed this plate. Then the next thing I did is the meshing, and I assigned the contacts between the parts. So if I go again in the contact manual, you see that let me see the geometry. Okay, I assign a local contact between the plate here. So the red is the master, so the rigid plate, and the part which is in blue is the slave surface of the contact. The one will be that will deform actually. So let's look quickly at the results. So let's look at the total translation. First, let's activate the full model. So using the symmetry plane option. So okay, on this side. Now I have the full wheel. And you see that when I push the wheel like that, it will deform, and I can then see the maximum deformation. So maximum will be 29 millimeter. Let's look at the von Mises stress. And okay, here it is. So this is at the end of the analysis. So you see that the red parts here is where I get the biggest stress. And okay, so this is all for this last example. So let's come back quickly to the conclusion and some advice to do a better nonlinear analysis. So I have a lot of tips because nonlinear is very that's not difficult, but you need to consider a lot of options. So first, perform linear analysis case before running nonlinear analysis. So by doing that, you will be able to judge whether or not you need to perform nonlinear analysis. So depending on the deformation. Parameter settings required for nonlinear analysis. Load increments are one of the most important of the parameter settings. So the parameters settings are really important, so you should care about that. The load increment, the number of load increment is important. So if you don't get the convergence, you can always increase the load increment and see what happens. Then convergence criteria selection also is important. Geometric nonlinear option. You can do subcase. You have the restart feature. Okay. Then next thing is the finite element modeling for nonlinear analysis. This is important also because in some cases you need to perform some special modeling for nonlinear in order to be sure that you'll have the convergence. It will be faster. So you can think about, for example, symmetric conditions. So in all the model I showed to you, it's always symmetric. Then you can use some shell, some beam in order to limit the number of elements. You can minimize the use of nonlinear material models, for example, if it's not needed. Create dense and smooth mesh in area of high strain. And when it's possible, use rotation or extraction filter to create hexa or penta element mesh to have better accuracy. And also pay attention to the mesh quality. So this is important because you'll get better results in bad mesh quality areas. Okay, it's all for today. I hope it was okay. And now I have, so today it's already almost 7:30, so I will take 2 questions. So if you have some question, please write quickly in this and I will answer in direct. Is there some question about all that? I hope you will, so this will be put on YouTube, so you'll have the video about that, so if you want to look again at all that. And we'll have a new, another webinar next week about fatigue analysis, so it will be a very nice webinar, the first one we do about fatigue. So I really hope that you will come to hear about that. Piotr Stepion will do it, and he prepared for a long time for this next webinar, and it will be really interesting. Also for the Italian attendees, we'll have some special webinar in Italian on Thursday. Okay, well, if I don't have any question, you can always send me by email or your question. So I think you know my email, cyprian@midasit.com. And see you next time. Goodbye.